I made this spreadsheet so that students could calculate the trajectory of an object flying through the air, but this spreadsheet includes air resistance. And often you see projectile problems where it says neglecting air resistance, but we really can't neglect it. It is an important factor. One thing I need you to understand right away is that if you go to the description in this video, there is a link to this actual spreadsheet. So you can practice as I go through the steps, and then after you create the spreadsheet, then you can change your variables. How fast do you want to shoot the object? What angle do you want to shoot it? What is the density of the air that you're shooting it through? And how high off the ground? You can change all those variables to calculate it. So the first two equations here is just simple kinematic equations, that the instantaneous position is going to be where it was initially added to the distance that it travels due to having some velocity for a period of time. Here, the instantaneous velocity is going to be what your initial velocity was added to your change in velocity, which is having some acceleration for a period of time. And then this equation here you don't typically see in high school physics, but I want to introduce it because it's really not too bad, and it opens up a whole new world of physics. This is called the force due to drag, the drag force. Often it's called air resistance, but I want to extend it to not just air, but any fluid, air or liquids like water, things like that. Let's see what variables affect the drag force. One variable is just velocity. That's how fast you're going. If you stick your hand out the window of a car going 10 miles per hour, you feel some air drag. But if you stick your hand out the window of the car going 50 miles per hour, you feel a lot more drag. In fact, if you were to go 3 times the velocity, you would actually have 9 times the air resistance or the drag force. Another variable that affects the drag force is the density of the fluid that you're moving through. Stick your hand out the window of a car going 5 miles per hour in air, you don't feel very much air resistance. But stick your hand out the window of a submarine going 5 miles per hour, you would feel a lot of fluid resistance. Another variable is the area, or the cross-sectional area, or the frontal area. Stick your hand out the window of a car with your palm of your hand facing down toward the ground. Your hand is slicing through the air and you don't feel very much drag force. But if you turn your palm so that your palm is facing into the wind, you have a lot more area and a lot more drag force. The last variable that affects the drag force is what's called the drag coefficient. So if we come over here to these shapes here, these 4 shapes, 1, 2, 3, 4, they all have the same frontal area or the cross-sectional area. But a flat plate is going to slide through the air a lot differently than a sphere does, or a prism, or a bullet. So there's different values for how well it slides through the air, and that is called the drag coefficient. The last equation is just simply Newton's second law, that if you add up all the forces, take the sum of the forces on that object and divide by the mass of that object, that will tell you the acceleration of the object. It's also called just the net force divided by the mass. So before we get into the actual spreadsheet, let's look at these questions here. It's kind of a circular iterative process here, but how fast an object is going to affect one of those 3 variables. And we already said that the faster you go, the more air resistance you have. And I have these cells set so that if you type in the right word here or the right formula over here, the background turns green so that you can just check and make sure you're on the right track. So the faster we go, the more air resistance there is. The more air resistance is, that's going to affect the net force on the object. And the net force on the object is going to affect the acceleration of the object. And then the acceleration of the object changes, well, how fast it's going, which changes the air resistance, which changes the net force, which changes the acceleration, which changes how fast it's going. So we have to keep track of this loop as we go through our spreadsheet. In this blue area here, we have all of our initial conditions. So how high off the ground was this thing initially shot? So it's like hitting a golf ball off of a cliff into the ocean, and the cliff was 50 meters off the water initially. And we're going to hit that golf ball at, say, 80.5 meters per second. We're going to do it at a 30-degree angle. Now, we are going to have to use sine and cosine to calculate the horizontal and vertical components of velocity. But spreadsheets are always in radian mode. Whatever angle you give, sine and cosine or tangent, has to be in radians. So I've typed a formula in here. Equal sign, say it's a formula. The formula is going to be radians, and then we just plugged in the angle to the formula. It will turn it into radians. This is the mass of a golf ball, the drag coefficient of a golf ball, the frontal area, that's just taking the diameter of the golf ball divided by 2 to find its radius, and then doing pi r squared. This is the density of air at sea level. If you were to shoot this golf ball or hit it, like in Denver, mile up, it's only about 1 kilogram per cubic meter would be the density of the air. And this is the acceleration of gravity. It does change slightly in different places on Earth, but this is a good average. I do have a negative here because we are going to have to keep track of whether its position is up or down. I should say whether its position, velocity, acceleration, or the forces are up or down, left or right. Up is positive, down is negative, left is negative, and right is positive. So here we go. Actually, one more thing. Let's come down to here and say we're going to shoot it with some initial velocity at some angle. And we want to calculate how much of that velocity is in the horizontal direction and how much is in the vertical direction. If you take the hypotenuse and multiply by the cosine of the angle, that would give us the velocity horizontal. And hypotenuse times the sine of the angle would give us this one here. So we're going to come up to here and come all the way over here. I've already said that our initial position in the horizontal direction is 0. But I have these cells here, first, second, third, fourth, fifth. That's the order in which you'd want to calculate all these. So the first one we would do is we're going to plug in the initial height. So it's going to be a formula, and I'm going to come over here and plug in the initial height, which is there. I do want to use dollar signs on that number. Dollar signs is just going to keep it from, it's going to hold it right there at that number. If I were to copy that formula to the right, the K wouldn't change to an L. If I copy that formula down with a dollar sign from the 6 wouldn't change to a 7. So dollar signs hold it there. I am using F4 on a keyboard that has function keys. So as I hit F4, I can toggle between those. If you didn't have an F key, like if you're on a Chromebook, you can just insert your cursor and type in a dollar sign there. Okay, so here we have our initial height. And then let's go ahead and find our current velocity. We shot it at 80 meters per second, but that was at this angle. We have to find out how fast it's traveling in the horizontal direction. So if I take the initial velocity with dollar signs and I multiply it by the cosine of the angle, and we can't use our angle in radians or in degrees, we have to use it in radians with dollar signs, that would tell us the component that is horizontal. So when we shoot it at 80.5 meters per second at a 30-degree angle, it's traveling horizontally at about 70 meters per second. We can find its vertical component the same way. This velocity with dollar signs multiplied by, this time, the sine of the angle in radians with dollar signs. And when we shoot it at 80.5 meters per second at a 30-degree angle, it's traveling at about 40 meters per second in the up direction. This velocity was positive, which means it's going to the right. This velocity was also positive, which means it was going up. Now let's go ahead and calculate the drag force, our fourth cell here. So we are going to put in the drag coefficient, which is here with dollar signs, multiplied by the area, which is here with dollar signs, multiplied by the density, which is here with dollar signs. And basically anytime I'm clicking in this blue area here, I want to use dollar signs, multiplied by the velocity. That's how fast it was going. Now we're trying to figure out how much drag force is in the horizontal direction. It depends on its velocity in the horizontal direction. Okay, and this time I don't use dollar signs, because as I copy that formula down one, it's going to have a little bit new velocity. So I want to have the velocity down here that corresponds to the drag force down here. That's velocity. It gets squared, so I hit Shift 6, which is raised to the power of 2, and then I can divide by 2. Now I made a mistake, and so I had it flagged here that there was a mistake in here. It says left, not right. And this was a positive value, which means the drag force was to the right, but its velocity was positive and its velocity was to the right. So we have to come back and adapt our equation by putting a negative number in there. A negative number is just going to mean the force was back off to the left. Okay, so now the cell turned green and the air went away. And these are just things I've programmed into the background of this spreadsheet to help you with this. All right, now we didn't have to be too careful with this negative here. Just as we shoot the thing off to the right, its velocity is always going to be to the right. We have to be a little more careful with the drag force in the up and down direction, because when we hit it initially, it's going to be going up for a while, and then after a while it's going to start coming down. So initially the velocity was positive, it was going up, but the drag force is going to be opposite of that. The drag force is going to be down and needs to be negative. When the thing starts falling down, the velocity will become negative, it will be going down, and the drag force opposes, so it's going to be going, the drag force is going to be going up, which should have a positive value. So sometimes we'll have a negative in front, sometimes we'll have a positive in front, and we're going to take care of that with an if statement. We're going to say if, open parentheses. So the way an if statement works, you say if a condition, if this is true, then this happens, otherwise that happens. So if this velocity is greater than 0, meaning if it's positive, we want it to be the result to be a negative number, meaning the drag force is going to be down. Otherwise, we want it to be a positive number. Okay, so that whole if statement is going to either be a negative one or a positive one, depending if the velocity is up or down. Now we're going to go ahead and multiply by all the things that calculate the drag force. So it was the drag coefficient with dollar signs, multiplied by the area with dollar signs. Oops, and I forgot the dollar sign there. There we go. Multiplied by the density with dollar signs, and multiplied by the velocity. That was this velocity. It gets squared, so raised to the power of 2, and divide by 2. So I just put all the formula in for that stuff there. And there we go. See how the drag force here was down, here the drag force was left, but the drag force, so there's 0.6 newtons in the down direction. Here there was 2.02 newtons into the left, and there was more drag force because it was traveling faster. All right, now we can go ahead and calculate the acceleration of the object in the horizontal direction. Well, there's only the acceleration is the sum of the forces, but in the horizontal direction there was only one force, and that was the drag force. And I want to divide that by the mass of the object. I don't put dollar signs here because as I bring this down, it will look down to the new drag force, but I do want to put dollar signs on this number because it's always, the mass of our object is always going to be the same. Okay, so that's going to be accelerating a little more than 4 times the acceleration of gravity, and that's because there is so much drag force on such little mass. So now we want to go ahead and find the acceleration in the up and down direction. Now we have to be careful. There's 2 forces in the up and down direction. There's the drag force opposing it, but there's also gravity pulling down. So we're going to add those forces. So this was the drag force, and it's already negative. I'm going to add to that the weight of the object, or the force of gravity. Weight is mass with dollar signs times gravity with dollar signs. Now I added this, but the gravity was already negative. So this was a negative number, and that's going to be a negative number. So they're going to get a lot of force in the down direction, and that's why it accelerated at such a big rate there. Let's see. So that's the sum of the forces divided by the mass of the object with dollar signs. Okay, so this is the acceleration in the y direction. Now we're going to come over here. I'm going to scoot over here just a little bit. We want to calculate its current position, where it's going to be 1/10 of a second later. So it's a formula. We start with an equal sign. It's its initial velocity. No dollar signs here, because as I copy this down, I don't want it to always be using that initial velocity. In this cell, this is going to be the initial velocity. So it's the initial velocity plus how fast it is going and for the length of time. So in the horizontal direction, this is how fast it's going, multiplied by the time. I don't want to just click on the time. I want to type in 0.1, because for every one of these cells, it's only going to have that velocity for 0.1 seconds, because we're going to calculate the new velocity every 0.1 seconds. Now we'll do the same thing for the vertical. So it's going to be its initial position, this one here, added to its velocity, which is here, multiplied by time. Okay, so initial velocity times time, and that's where it's going to be in the y direction 1/10 of a second later. Its current velocity is the same thing here. This instantaneous velocity right here is going to be its initial velocity, which is just one above it. That velocity added to the acceleration. This is the drag force, but this is the acceleration. We're doing the horizontal velocity, so we need to use the horizontal acceleration. And it was only accelerating at that rate for 0.1 seconds. And then we'll do the same thing in the y direction. It's the velocity plus acceleration times time. So it's this velocity plus, that was in the y direction, it had this acceleration for a time of 0.1 seconds. Okay, so it's slowing down. It was shot this fast, a moment later it's a little slower. It was shot up at that speed, a moment later it's traveling a little slower. Now, here we see we have 12, 12, 12, and 12. This equation was calculated based upon all those constants over here and how fast it was going. And the same thing here. So I can just select all 4 of those formulas and copy them down at one time. Okay, and so this cell here now calculates the drag force based upon that velocity. Now that we've got all of these cells on this line and correct, we can copy it all the way down. And I'm going to copy it all the way down for, I think, about 15 seconds. There we go. And this is all of our numbers here. I'm going to go ahead and reduce that a little bit so you can see more of it. And lots of numbers there to calculate. I did go ahead and create this tab here, which is a graph of the horizontal position and vertical position. And so if we shoot this thing at a I think it was 80.5 meters per second at a 30-degree angle. It's going really fast, and every one of those dots is at a time of 0.1 seconds. So it's not traveling very fast in through here and starts to pick up a little bit of speed. The beauty of this sheet is that I can go back and change some of the initial variables. If I wanted to shoot it at 150 meters per second, now these cells here refer to that. So just changing that changes all those cells, and it changes my graph, and it goes like that. If I were to come back to here and shoot it not at a 30-degree angle, but maybe a 10-degree angle, and this time let's shoot it at, say, 350 meters per second. That's right at the speed of sound. And so we're going to go here, and it's going to go sheesh, way out here. So you can, after you've done this spreadsheet yourself, you can play with these variables. You can change the drag coefficient. I've given you for a couple different shapes, but you can look up on the internet what drag coefficient you want for the object you're shooting. If you're going to be shooting this up in a high elevation where the density of air is less, look up what the density of the air is. And you can change the variables here, and it will change everything there. This is a pretty neat spreadsheet, very powerful. This is getting really close to predicting exactly where it's going to go. I should say that this is still just an estimate because the velocity doesn't change every 1/10 of a second, and the drag force doesn't change just every 1/10 of a second. It is changing continuously. So to do this more accurately, we would need smaller intervals of time and more cells, or calculus would do a really good job of that. Hope you enjoyed.